So, let's briefly repeat what we have seen so far. We have seen how we have strategies represented as relations. We've seen that we need to make them deterministic. And we've seen one approach based on simple cofactor computations of how we can actually achieve this determinization. Now we are going to look at a different approach. And this one, the learning-based approach, is actually the one that, to our knowledge, worked in our synthesis tools best. So we have tried really a whole lot of things with all kinds of different optimizations. And this, despite its simplicity, also is what we have achieved the best results with so far. In principle, we have almost completely the same loop as before. The only difference is here in this line. So here before we used this care set that we can compute from can be 0 and can be 1 to just find a small BDD for in between these two sets basically. And now we use this can be 1 and can be 0 to define the boundaries of what our function is supposed to be, and we are going to learn a function with so-called computational learning. Computational learning basically works in the following way. You have a learning algorithm or student, and you have an oracle called the teacher, and they interact with each other. And the idea is that the student can ask the teacher questions and ask something like, he guesses some value for the function, so it says, is this guess for the function correct? And then the teacher, using these sets can be 0 and can be 1, checks this guess by the student and says, no, this guess is not correct, so because for this input vector x3, your function produces a 1, but it should be a 0. And then the student uses this information to refine the guess, because he now knows one more data point, so he can make a better guess. He asks the teacher again, is my next guess, f1, is this correct? And then the teacher says, nah, for x8 your f1 gives a 0, but actually it should give a 1. So the student updates the guess again and makes another one and asks the teacher, is f2 correct? And then the teacher says, yes, this guess is correct. And this is basically what learning does. So the teacher, having these sets, if you look back, having available these sets can be 0 and can be 1, if I get a guess, I can use these sets to check if this guess is correct. Or if there is some input vectors for which the guess would produce results that contradict these two sets. So it gives a 1 somewhere where it cannot be a 1, or things like that. And since this is so much fun, I suggest that we try this out in practice. So I need someone to volunteer as a teacher. Yeah? Okay. Will you come to the front? I'll give you this, don't show it to the others. Okay, then just take some more paper. This one, take this one I don't need. Okay, so to make it easier, I'm going to tell you that we are going to look for a function that has two inputs, a and b, and only one output, y. And we want a formula representation for our function. So we want something y equals in terms of a and b. So now you will make guesses, and you will then, once a guess has been made, tell them if the guess is correct according to what you have on your sheet, or otherwise give them a counterexample as we have seen on the slide, okay? First guess, please.
Is y a?
Okay. First guess is YA. What's your answer?
No.
The answer is no. Okay. Why not?
I have to give a counterexample.
Yes.
Because there's...
You need to give one input vector, one set of values for A and B that contradicts this formula.
So there is one input vector where A is 0 and B is 0 and Y is 1.
So 0, 0 should map to 1, and that would not be the case if this was true. So what's your next guess?
Not a.
Not A.
No.
Why not?
Do I have to give all possibilities now or just one?
One will suffice, but obviously you can't give this one again because for this one it would work. For 0, 0, not A would be 1 and it should also be 1. So now you have to find a different one.
Okay. There is an input vector with A 0 and B 1 and Y is 0.
Okay, again, this would contradict this formula because not A, if A is 0, would be true, but the input vector 0, 1 should map to 0.
Not b.
Not B. Yeah, okay.
Okay.
No.
There is an input vector A1, B1, Y0, Y1.
Not A, X or B.
Just a second. Not A, X or B cannot be a valid guess because they would already contradict this one.
Thank you.
Because not A is 1, X or 1 is... No, sorry, that would actually work, right? Not 0 is 1, X or 1 is 0, no. So that's actually a valid guess. What is it? Not A, X or B?
Oh, I meant not in not parentheses and
okay.
X or B.
But that will...
It means...
Is that consistent with this one, this one?
Yes.
It should be equivalent
Yeah.
of A and B.
Okay.
A equals B.
A
Yeah.
and B?
No, A is equal to B, so the value of A is the same
and B
value
are
as B.
not A and not
They're equal.
Yeah.
So you only have to check if
Yeah.
1, 0 gives
Yeah.
0 or 1. This is your only possible counterexample.
Right. Now you have to look at this line.
Yeah.
Because here if you compute the x or it's 1, if you negate it, it's 0, so the output should be 0, and here it's...
Yeah. It's no.
So no, because 1, 0 should give 0.
A or not
Then
b.
yes.
I think the line should actually... Shouldn't it be no, because 1, 0 actually
It
gives
gives
1.
it 1, yeah, sorry.
Yeah.
A or not b.
Philosophy for C.
A or not B?
Yeah, that's correct.
Okay. Thank you. Let's see. Let's try another one. I will need another volunteer. Yeah. This time we'll make one with 3. You can pick someone to help you if you want.
I will try.
So, first guess.
A. No. Because there is a set A is 1, B is 0, C is 1. No, C is 0. Sorry. 1, 0, 0, and it's 1.
No, it's 0. 1, 0, 0 gives a 0.
Not A or B or C. Kann ja fast nichts anderes mehr sein.
I think this guess is actually correct. Okay. Thank you. No fun. Because what I actually wanted to show with this slightly larger example is that if you're just guessing randomly, as we have already seen with the simpler one where we needed quite a few guesses, this can take some time, and obviously if you have many variables you cannot just go through all possible combinations. So, and also it becomes harder and harder to make guesses that don't contradict one of the examples that you already have. Because if you contradict one of the examples you already have, the teacher might just give you this example back and you haven't learned anything new. So the teacher is not obliged to give you a new counterexample if one of the old ones already fits. So what we will basically need is a more structured way to make our guesses. And for that I'll show you a learning algorithm with which you can learn a conjunctive normal form in a structured way. This has two advantages. First of all, the guessing is now in some sort structured and therefore much faster to terminate. And also what you will get is already in a conjunctive normal form, which has many advantages for several applications. So how does this work? We will again start from our sets can be 0 and can be 1, but for notational convenience we will now negate them and call them must be 1 and must be 0. Meaning should be obvious. If it cannot be 0, then obviously it must be 1 and the other way around. And what will we do? If we want to learn a CNF, we will always start with the constant true as a first candidate. And then we will step by step exclude things where it should not be true. Because as you know, a CNF is a conjunction of things, so every clause will cut away a little bit where we were too much true until we reach something that is kind of okay. I'll have a graphical representation in a minute so you'll see how this works. So you'll say, you start with true, and then you make a loop while your guess is not correct. How can you check if the guess is correct or not? You just check whether your current guess n intersected with where it must be 0 is satisfiable. So you can implement this with a SAT solver or with BDDs or whatever you want. Because what does this mean? This means your function will produce true for an input where you must give 0. And obviously that means something is incorrect. If this is satisfiable, you look for one assignment that satisfies this equation, which is then your counterexample that you can use to make an updated guess. This is also why it is so important that SAT solvers are capable of giving you satisfying models, because this is exactly what you need here. A satisfying model would exactly be what this function gives you. And then you just say, okay, then my function is f and the negation of this what I just had. Since this b is a conjunction of variables, the negation of b will be a clause. So when f is in C and F and I add this clause, I will again have a C and F and I can just try again. So graphically speaking, so that this becomes all a bit more clear, let's say the blue area is where f must be 0, the green area is where f can be 0, and the white area is where it obviously must be 1. And we start with guessing that it is 1 everywhere, which is obviously incorrect because in the blue area it cannot be. So if we make the intersection of f and must be 0, so initially f is the whole rectangle, and the intersection with the blue area then is just the blue area, then this is obviously satisfiable because there is a whole bunch of things in here, and we just pick one possible assignment that makes that's in this set, and then we change our f, meaning that okay, for this point f will no longer be true, because we said okay, f is true everywhere except in this what we just picked. And then we again make the intersection between the whole rectangle minus this point and the blue area, which is still an awful lot, so we will just get some other point. And then we say, okay, then we exclude this. And then we pick another one, and we exclude this. And another one, and we exclude this, and so on. And you can already see this will not scale. Because in every iteration we exclude exactly one assignment. How many assignments are there? Well, 2 to the power of the number of variables that we have, potentially. Obviously not all of them will be in this blue area, but a large portion of it will, and therefore this will most probably not work. So we will need something a little bit more elaborate, and we will optimize it by generalizing the counterexamples a little bit. Again, let's go through the algorithm and then we'll look at the graphical representation, and then it should become much clearer. These 3 lines are new now. So what are we going to do? We are going to try to generalize the counterexample, which means we are going to try to remove a few literals from this cube to make it more general. How do we do that? Well, we just try leaving out one, and then we check if this still doesn't intersect with the set where it actually must be 1. If we leave this one out and we're still only in the area where everything must be 0, then we're good. If not, then we would exclude too much and we can't do that. But if we can do that, then we do it, and then we try this for the next literal and so on. Let's look at it graphically. So again, we find one counterexample. We say, okay, for this dot, it should actually be 0, so we should exclude this from our function f. But now we try to drop one literal from this cube, and what happens? The region gets larger. Because now we have one variable less that restricts this red dot, and so it becomes slightly larger. It covers more assignments, because this literal that we left out can now take both values and it will not make a difference. Then we try to leave out another one, and another one. And still all the time we are just excluding things from the onset where either it must be 0 or it can be 0. So it doesn't hurt to exclude all these things. But as soon as we would have this red area intersect with the white area here, we would have excluded too much, because then f would be 0 somewhere here, but it should be 1 out here in the white area, and that would be too much. So in that case, we cannot exclude this literal. And we add it again and try the next one. Until we cannot remove any more, then we just pick the next dot. And again, we try to generalize this one and drop a few literals and grow this one. And then we try to see if there is still something in the intersection of F and the blue area, and we get this dot. And we enlarge this one, and then the last one, and we enlarge this one. And now if we try to see if there is an intersection between F and the blue area, there is no more, because F is only true outside of this red area, and the blue area is already completely covered by the red area. So now we're done and we have learned the function. And obviously, as you could see, this was way faster than covering the blue area with all single dots. Because dropping these literals is rather fast. You just go through the list of literals once. Okay, you have to do a sat call per literal that you want to drop. But still, this is way, way faster than enumerating an exponential number of literals. And this is how you can, in a structured way, learn a conjunctive normal form from sets that are given to you. Now, as your homework until, not next week, because next week is 1st of May, but until in 2 weeks, is to write a DNF learning algorithm. So basically, I can do this in the same way as I had it on the previous slide. So you can just write some pseudocode plus some hand-drawn sketches and explanations. Doesn't have to be very fancy. You can also work in groups, in the same groups that you also use for the practical tasks, but you can also do it alone if you prefer, or for whatever reason, no problem. And just as a tip, disjunctive normal form is always exactly dual to conjunctive normal form, so basically by switching everything that is true to false and conjunctions to disjunctions and stuff like that, it shouldn't be that hard. Okay, any questions? None. On this slide, I just realized there is a typo. Yes?